Okay. So here we stopped, right? Diksha, Mokshi are joining together in a same screen.
Sir Mokshi is joining.
Okay, so here we stopped. Do you remember the procedure? Any one of you? Some. Do you remember the procedure? The overall Hartree-Fock procedure in Hartree-Fock-Ruthven procedure. No, I'm asking qualitatively, not the mathematical formulation. No matter. So what this is how we arrive. So let's explain from the beginning that what we have done so far. If you remember that we are now talking about how to deal a molecule. Okay. So now let's recap what we have so far. What we have done. We have a molecule which is having some atoms somewhere, right, and some electrons somewhere around. Okay, we don't know exactly where they are because we cannot locate them. So let's say we begin to consider that we have n number of electrons. Okay. Total Hamiltonian will have kinetic energy of each electron, each atoms, and their interactions in it. If you remember, first thing we did, we have invoked the Born-Oppenheimer approximation and separate the electronic Hamiltonian from the nuclear Hamiltonian. Right? So what we have done is BO approximation. In this approximation, with the usefulness of this approximation, that if you have, let's say, a molecule like water, what it does when it treats electron, it considers that the atom are fixed. The moment you invoke the view approximation, you get a particular geometry of molecule where atom position are fixed, right? So first step is view approximation. Then second step, you have, so from there you get electronic Hamiltonian. So total Hamiltonian will be, electronic Hamiltonian will be that sum over whatever I have, I hi plus sum over of ij on upon I. This is electronic Hamiltonian plus addition. We have a nuclear repulsion term. Since there's a constant for view approximation, we did not treat it separately. We just can calculate this constant, and at the end we can add to the electronic energy. Right? To compute this part, H electronic psi electronic equal to electronic psi electronic. To compute this and this corresponding function, we invoke Hartree-Fock theory. Right? We have done details of that. It's a variation theory, and we have done a lot of mathematical, derivations to arrive the final equation. What is final equation? In non-canonical format, FC equal to SC, right? That's what we derive. B, what is C for here? So once you do Hartree-Fock theory, what you get this equation, and also this equation comes from another equation which is electronegative, which is f of psi I equal to epsilon I psi. So Hartree-Fock theory will give you this equation, right? What is f? F is the spherically average Fock operator. Like this. From here, I get f of Ri psi I of R1 R1 equal to, this is 1, this is I, equal to epsilon I psi I of R1. Right? What is psi I? Psi I is a spatial orbital. Right? This is spatial orbital for the molecule. So whole molecule is considered, and then we solve this equation. After doing spin integration, we get this. Right? Psi I. Psi is a space orbital. Now, so psi I, I don't have one, I have set of that, right? Depending on how many electrons we have, this will be n by 2 occupied, and there will be infinite number of virtual, right? So this, from this, if we include here, I get orbital energy and the function back. The problem is I don't have a form of psi I. I don't have a form of molecular orbitals. So how do we write? We have written psi I as a linear combination of C mu I phi mu, right? Mu equal to 1 to a set of predetermined number of atomic orbitals. If I have water molecule, I'll take some orbitals for hydrogen and some orbitals for oxygen, right? That set we'll write as linear combination to get a molecular orbital, right? This equation also ensure that these molecular orbitals are orthogonal to each other. But atomic orbitals are not, right? So using this condition, we put it here. If you remember the complete derivation, this we put it here and get, instead of one equation, we get n number of equations, right? Every time, so we put here, right, f of R1, then sum over of mu C mu I phi mu equal to epsilon I sum over of mu C mu I phi mu, right? So number of equation depends on what is mu, right? Mu runs from 1 to k, a predetermined set. So total number will be k. So this is not one equation. There are k equations here, right? To get each equation, we have written them in the matrix form. So what you do here, you pre-multiplied with, you project with phi mu. Projection means pre-multiplying and doing the integration over the coordinate. And this, I hope you can remember this. This is the procedure that we are talking about yesterday. After doing this, and then we write them in terms of matrix form, we get f of c equal to SC, right? What is S here? C is a coefficient matrix of this kind, right? What is S? S we get as phi mu star, let's say R1, phi mu of R1, BR1. This is the S, right? Because atomic orbitals are not orthogonal to each other. If they are same orbital, this is one. They are normalized, but they are not orthogonal. So if mu and nu are different, it will the value of S will be between. So this is like I should write in a small way. I should this is mu. If mu and nu are same, the same index, same orbital, s equal to 1, s mu nu equal to 1. If they are different, I get a value. That value will be minimum 0, maximum. I mean, minimum, it will be 0 to 1, minimum 0, maximum. It will be in between, right? Okay. So, but this is not very useful. This equation, solving this equation was problematic because this is not an eigenvalue equation. You notice this. This is not an eigenvalue equation. So solving this is difficult. To make it eigenvalue equation, what we have done, we have orthogonalized this. Right? How did you orthogonalize this? That's a method of orthogonalization is this. We have taken any matrix, let's say x, and then if you do s x, we get that equal to 1. Right? So we chose a matrix x such that this transformation satisfies. Right? And then what did we do? We have defined, so in this transformation, we have defined a matrix C, transform C, we make it as X. How do we get X? X is a matrix that make S as orthogonal, right? Any matrix can be orthogonalized. As in linear algebra problem, any matrix can be orthogonalized. We have orthogonalized the matrix S with a transformation matrix that is X. Now we define a new set of C such that C prime equal to XC. What is C prime? In C prime, S is orthogonal. So now what we have done, we made this equation as if C prime equal to, sorry, this is f of xc, this is equal to s xc. And then what we do? We have done this transformation if xc equal to x prime s xc. And that's our definition. By definition, this is equal to 1. Right? So using that relation, what we got, this will give you a new transformation. This is a new transformation matrix. Transform matrix. I get if this. No, no, I have done something. I think a mistake. What was the mistake? C equal to the small error. X prime. X prime. I get prime here. So what we get from here is f c prime, f prime c prime equal to c prime. Right? What is f prime? F prime equal to x dagger f. If you have an equation in this form, this is a linear matrix eigenvalue equation. If you diagonalize f prime, you get c prime and diagonal matrix. Right? So what next step? You diagonalize f prime to get c prime, right? And with this c prime, you convert into c. What is c? Then you get c equal to X, right? And then what we do? We construct, now we construct again new F. What is this? This, if you remember, I have H new at the other way, not conjugate part. I had mu 4 plus, if you remember that, that was sum over of, what is the term I am using? Sigma delta, right? It was double sum, so sum over sigma, sum over delta, and then we had these two C, what I've done, C sigma B, C of delta V, right? And then we have this guy, they are multiplied by 2. Then we have this guy, what is the term? Mu sigma, and then mu delta minus half of mu sigma delta U, right? Now you see we got C. From this C I can construct this. So this was written as is mu 4 plus sigma delta. This was written whole thing as P is that sigma delta, right? Now what do you need to do? We have C. From that C, if you put here, I get P. So I have a P now. From that P, this is already calculated. From this P, if I calculate this whole quantity, I add them, I get F. Once I have F, I have now FC equal to SC, the whole problem, right? And then you construct, you diagonalize this. From here, you get F prime C prime equal to I mean C prime E. From that, so by means of X, from that you get C prime, right? And this C prime you use to construct P sigma delta again. From there you construct F, right? And then you solve this FC equal to SC. Again, same procedure. Keep on doing it. You have to stop it somewhere. How do you stop? You see whether two consecutive, that is P sigma delta, let's say one iteration I, and P sigma delta some iteration I minus 1, they are less than a threshold. You keep on doing that till that point you stop. So what do you need? You first need to use Born-Haber approximation to fix the molecular atomic coordinates. Once you have atomic coordinate, you need to construct this guy, right? You need to have this set. Molecular orbital you don't know how to get, so you get a set of atomic orbitals. A set, preferably larger, right? Once you have that, then you have to get this equation. To get this equation, what you need? You need this. You need F. I'm sorry. You need F. For F, what you need? You need this term. You need this terms, and you need this. That's the first thing, right? That what we need, what all we have. We You see, when you fix the molecular geometry, what you have? You have set of atomic orbitals. From that set of orbitals, you can always construct and always calculate these terms, their integration, right? What is this? This was integration of in the atomic orbital phi mu star h of 1 phi mu dr of 1. You see, this is definite integrals, right? From 0 to infinity or from minus infinity to plus infinity, whatever the it is usually 0 to infinity for atomic calculations, right? So you can evaluate this integral, you can calculate this integral, and then this is also an integral, this guys. What is this? This is sigma star 1 sorry, mu star 1 mu of 2. These are star 1 upon r1 2 mu 1 delta 2 dr1 dr2. Right? This guy is basically this. Right? What are these? These are that atomic orbital atomic functions. You need atomic functions. That's all you need. So from there, you can calculate this integration. So this term and these terms can be calculated if you know the position of the atoms. You see the atom position dependent. These function depend on the position of the atom. Right? If you solve hydrogen atom, you put hydrogen atom at the center and then you have R. Here you cannot put hydrogen atom at the center. You have to form from the center of mass of the molecule. Right? So let's say I have water molecule somewhere center of mass. From that mass, I have to find the position of oxygen. And with respect to that position, I have oxygen atomic orbitals. Right? So if I know this atomic position, I can easily find out their orbitals. If I have the atomic orbitals, I can calculate these integrals. These are called 1 electron integrals. These are 2 electron integrals. One is Coulomb integrals, one is exchange integrals. There are two different type of 2 electron integrals. You can calculate them. What you don't know at the beginning is P, right? The density matrix. You consider, you guess a density matrix. Just guess. It may be zero. Zero means there's no two electronic part. You may guess this density from a Huckel theory, where you only have pi electrons, right? So from anywhere you can guess it. Once you guess this P, then you can easily construct F. Once we have F, then S is also known. Once I have a set of psi, a set of phi, I can calculate S. With the guess P, I can calculate F. So I have now Fc equal to Sc. Then I have to diagonalize S. There are different routines to diagonalize. Right? One is canonical diagonalization, one is Lagrange diagonalization. So use any of them to diagonalize. If you diagonalize, you get X. From that X, you construct F prime and C prime. Right? You get F prime C prime equal to C prime A prime. Solve this, diagonalize that. You get a set of C prime. From that C prime, get back to C. Once you have a new C, now with this new C, you construct new density matrix. This is no longer guessed. This is a calculated one. Right? Obviously, it must be better than the guess one. And then with this, you keep on doing the same procedure unless until two density matrix, two guess matrix, they converge, they are same within certain threshold. Once you have that, your Hartree-Fock theory is complete, right? So that's how Hartree-Fock theory. That's why it's called self-iteration field procedure. You are doing iteratively till it gets consistent with itself, right? That's the basis of most of the self-iteration iterative procedure, most of the self-iterative SCF methods. But in Hartree-Fock we do it. Okay. And how to get S, that also we have discussed yesterday. We have S, we need to diagonalize this, I'm sorry, to get as unit matrix. One choice of X, as we have done that, what was that? S inverse, right? Is half. Minus or plus? Minus. Then I pose a question, how to get is to the minus? How to get a functional matrix? Right? A simple technique is there. You see, any matrix, let's say A, can be diagonalized by, I have any matrix A. If I do this transformation, U inverse A, U. What is this? This is a matrix that will be diagonal, right? Now, if I do the reverse transformation, if I do something like this, U inverse A, U inverse, then what I get? I get right side as U A diagonal matrix, right? This is left side what I get. I get back my A, and right side I have A the diagonal. So you can diagonalize the matrix, you can undiagonalize it. What is the meaning of diagonalization? The meaning of diagonalization is the solution. Right? So a set of linear equation, when you solve it, you see what information, you don't get any new information after solution. You just get the value of x, y, z such that all three equations satisfy. If you have n by n, you get n solutions, n values of n different variables such that all n equations satisfies. Right? So diagonal is a special case of the matrix. Right? Now, if that is the case, now you can take any function of diagonal form. If I want to get square of any matrix and that matrix is diagonal, then it's a square of each element. I hope you understood this. Let's say I have a matrix something like this: A1, A2, A3, all are 0. This is A, or let's say this is X. If I want to get X square, since all elements are 0, you multiply this matrix with same matrix, you get the diagonal element square. Right? If I want to get a function of this matrix X in the diagonal form, you get the function of the diagonal element. That's all. So if I want to get something like X half, what I get? I get root over A1 0 0 0 root over A1 0 and so on. That's easy. Now if I want to get this matrix which is not diagonal, what I have to do? I have to undiagonalize it. So what I am trying to say is I want to get a function of A, right? Let's say I want to find out A square. So what I first do, I will first diagonalize this matrix to get a diagonal matrix. And then get A square, a diagonal matrix square, by just squaring the diagonal elements. Now I want to get a square. So what I do? I just take square of that and undiagonalize it. So what I mean, this can be also, let's say I am after getting this, then I am doing a square, right? So this matrix. And then if you use same, so this is a matrix will be A1 square, A2 square, AN square. If you undiagonalize it, if you have something like now you do u a I or a square u inverse, this will be equal to, right? So procedure is same. Everything can be done. All you need to do just diagonalize the matrix. And rest part is easy because once you diagonalize the matrix, you know what is u and u inverse, right? Once you know u inverse, you can always back diagonalize it or undiagonalize it to get the original matrix function back, right? So that's the procedure. That's how we are going. We solve. We get this x to the power of half, right? So I'll just do one thing. There's another way to diagonalize. You consider s equal to u inverse small. Small s is the diagonal matrix elements of that, right? So this is called Lagrangian diagonalization. And this is the canonical. That is symmetric. This is called canonical. Nothing called Lagrangian diagonalization. This is called canonical diagonalization, right? There in Jabu both are there. Ideally, we follow most of the packages follow this one, right? But they are same. They must give you the same answer, right? Now, what we don't know here yet, why that P is called density matrix? That's the question. Is it clear from there? Why P is not is called a density matrix? That question is still not there, right? So let us. So the answer is still we don't know. Let us answer that. What is density matrix? What is it? What is electron density? Let's say I have some electron here, some orbital here, occupied by one electron. The same orbital can be occupied by
Sir,
another electron. Right?
sir,
Yes, Mokshi.
sir, I wanted to ask
Hmm.
the portion where you explained about undiagonalizing the matrix.
Hmm.
You squared the matrix and then the expression you write u a square u inverse. How you undiagonalize? I didn't understand
You
this.
see how to diagonalize it. A, you diagonalize it by an unitary matrix, this transformation, right?
Yes, sir.
This will be a diagonal matrix, right? Now, how do you undiagonalize it? You get u inverse A, u inverse equal to u a u inverse. This is a diagonal matrix, right? So you get a, right? From here, you get ai square. If you want to undiagonalize this, the transformation is exactly same. So same procedure we follow. We get a square equal to the transformation matrix is exactly same. This is a square. See for diagonalization, what we do, we take inverse of unitary matrix, the unitary matrix. The undiagonalization is just opposite. You left side you do unitary matrix, right side you take inverse of the unitary matrix. It's just the opposite transformation. The u must be same. Did I
Okay,
answer
sir.
your question?
Yes, sir. Yes, sir.
Just once you diagonalize it, you know what is u. And then after diagonalizing, you take the function of diagonal elements. You form a new function which is itself also diagonal. From there, you undiagonalize it with the reverse transformation. Instead of u inverse au, you take u a u inverse. That's all. Okay. So the next question I asked that what is electron density in a molecule? Let us give me an example. Let's say hydrogen molecule is there, right? In the LCO picture, I have one orbital here and another orbital here, right? Our old classical qualitative picture. Let's say I want to calculate electron density at this point, right? So this point can also be spread over by this orbital, and I'll also have this orbital. So orbital means it will start from zero nucleus, it will go to infinity. So at any point, both orbitals will be coexisting, they're existing, right? So if you want to calculate electron density here for that particular orbital, then what will do? The electron density rho will be psi a of star psi a. This is equal to modulus of psi a square. If I want to get a density function, then I have to do rho of r dr equal to psi square dr. What is this? It is the electron density between 0, between r and r plus dr. That's the electron density probability function, right? That any function we write. If you want to get the value between from one point to another point, we take that point as dr, and then from there we get a segment dr, right? So dr is a volume element. So that is the density function, right? Now, if you want to get total density, total electron density, then how much should be? I should integrate this rho r, I'm sorry, small rho r dr. Right side, how many electrons are there? How many orbitals will be there? Not one or two. See, this is for one orbital, but I have n number of orbitals, right? In space coordinate, I have n by 2 number of orbitals. So I have n by 2, I mean, sorry, 1 to n by 2. Equal to 1 to n by 2. Now each orbital can have 2 electrons. So I can have 2 here. Right? Now we should get this modulus of psi a square dr equal to 1 to n by 2. You see, each orbital is, I have to put an integration, right? Each molecular orbital is normalized. So psi a square for each a will give me 1. How many I have? N by 2. So this will give me 2 into n by 2. Right? When a equal to 1, I get 1. When a equal to 2, I get 1. When a equal to n by 2, I get 1. So I get total n by 2. 1 plus 1 plus 1 up to n by 2, I get n by 2. Right? So if you don't understand this, let me write here. This will be I equal to 1 to, or a equal to 1 to n by 2, just 1. It will 1 plus 1 plus 1 up to n by 2. So I get a 2 into n by 2, this is equal to n. What is n? The number of electrons. That should be the charge, of course, right? If I start with number of electrons, we must get number of electrons. If we integrate total probability of finding the electrons, right? So this is the density, right? This is the charge density over point r to r plus dr. This is a volume segment, right? How come this is related to our C mu nu and so on? Let us do that. Now what is psi star a, psi a? Right, in atomic orbital. What we write at atomic orbital? This will be nu. Now let us have that same notation. It was sigma C sigma a star, right? Phi sigma, and C delta a phi delta, right? This you write in terms of This you write in terms of, so there will be another sigma delta. This will be sigma delta I'm sorry, sigma A star delta. This is A. C sigma A star C delta A phi delta star phi phi sigma star phi delta. Right? Now if we get rho, is this 2 into A equal to 1 to n by 2, I get modulus of psi is square. I get sum over of 2 A equal to 1 to n by 2, sum over of sigma, sum over of delta, C sigma A star, C delta A. That's all, right? Now if you put here, somewhere here, you see this is the guy. Now I have to write it. This is sigma, this is delta, this is, you see, I star, sigma star. You see, this is the guy that we have taken as P, right? So this is directly related to the charge, density of charge, right? Density distribution function. That's why it's called charge density matrix. Okay. Now, next question is what are phi? How to choose the phi? Atomic orbitals, right? How to get the atomic orbitals? We can get atomic orbitals for hydrogen by solving hydrogen atom. How can we get atomic orbital for oxygen or sulfur or some other atom? How do we get it? Hydrogen atomic orbital you can get sp1s, 2s, 2p, 3p, all are hydrogen orbital. They are not orbital of carbon. How to get orbital of carbon? Hydrogen like. How to solve the hydrogen like? You get an orbital, right? Hydrogen like orbital you get. You have just more amount of nuclear charge. J will be more. So that will be hydrogen like orbitals, right? We don't need a function. We don't need the precise orbitals. We're not solving for water, we're not solving oxygen, we're solving water. So for oxygen functions we need, there should be atomic orbitals. They're not necessarily the exact function of oxygen atom. They're set of orbitals. If we have no exact function of oxygen atom, then problem is solved. You're solving anybody problem. That is not anyway possible. So what you do, you take hydrogen-like orbitals. You solve hydrogen atom and take the orbital with larger amount of Z. Hydrogen orbital you can solve with Z equal to non-zero, right? You put there, for oxygen you put 8 and so on. You get a set of functions after solving hydrogen atom. That can be taken here, right? If you take those orbitals are called Slater orbitals. Slater first did that. So this can be the two types. This can be Slater orbitals, right? If you know this, the form of this function, you can easily calculate one electronic integrals and two electron integrals each 4, and that's two electron integrals j and k, right? You put there, that's all. So what you need? You need a set of functions. You need a set of bases where you construct this electronic integral, right? So these are called basis set. Right? So that's how the beginning, the initial calculations are use only scatter orbitals, which gives accurate results, because the atomic orbitals, they do really like look like hydrogen orbitals. However, these calculations are much more difficult to do and more time consuming than computation, more expensive. Later on, Popper and his student boys, they came with a much better idea. They said that we just need orbitals. We need one electronic function. If we don't take Slater, what is Slater orbitals, by the way? They look like, and they look like, this will be looking like uh, x to the power of m, y to the power of n, z to the power of, let's say, m and l, and exponential of xi. R is the distance between the electron from the center of mass, right? X, m, n, l, if all are zero, it is s orbital, right? If together equal to 1, it is p orbital. So either x can be equal to 1, I mean m can be equal to 1, n and l equal to 0. All are, you see what I'm trying to say here, tell here is now that quantization, quantum number, right? I should not put L here because that's a specific to quantum number. M, let me put uh, M, N, O. So M plus N plus O, this will give me the quantum number L, angular quantum number, right? So this is the Slater orbitals. What these people came with a better idea. They said, okay, this I'm not going, we are not going to use. Instead, we are going to use similar thing, Z, O. Instead of this, why not use this? Okay? So instead of exponential minus r square, we are going to use r square. This set of function, as you know, this is a type of function. These are the Gaussian function. Okay? So these people suggested the use of Gaussian function. Why this is beneficiary? This is advantageous because you see what I have to do. So I have a sigma, which is a Gaussian function. I have a mu, which is another Gaussian function. I have mu, in this case mu, that's what we are used, doesn't matter the dummy variable, 1 upon r1, 2. I have delta 1 mu 2, right? What is the advantage? Advantage is if I use two Gaussian, so this is a Gaussian, this is a Gaussian, this is a Gaussian, this is a Gaussian. Product of two Gaussians is a single Gaussian. So take this example, let's say I have a Gaussian to the power of minus xi 1 r square, r1 square. I have another Gaussian to the power of minus xi 2 r2 square. These two are two different s function. Let's say one for carbon, one for hydrogen. Then if you multiply this, what you get? You can going to get sum of epsilon 1 plus epsilon 2. Sorry, this is equal to the minus of epsilon 1 r1 square minus epsilon 2 r2 square. This can be done in new coordinate form. I can write exponential of Jai or you can prove that. Product of two Gaussian from two origin will be a single Gaussian. Right? So this together, if you take a product, there are two functions. Now I'll give one function. Here I get two Gaussian product, I get one product function. And then you could multiply together, instead of four Gaussian, you get only one Gaussian. Right? And then you're going to integrate over only one Gaussian function. One function you're integrating. You see, this is a huge advantage. Instead of integrating four different functions, you are just integrating only one function. So integration evaluation become much faster than before. Ideally, quantum chemistry start from there. The computation become feasible. With latter, it was accurate. It was feasible for small system, but for large system it was impossible. Once they put Gaussian type orbital, things become
Excuse
much
me,
more
sir.
easy. Calculation starts.
Excuse me, sir.
Yes.
Sir, how this logic is not suitable? Suitable.
For this one, you see, I will give an example. This is the derivation I don't want to do. You can do it. It's there in Java, but I will give you the example of plotting example. Right? Let's say I have a Gaussian. A Gaussian looks like this. That you know, right? Another Gaussian which is close to this will look like this.
Yes, sir.
If you multiply this either to close, then from the constructive interference you should get a Gaussian which will look like this. Color not visible.
On multiplication.
So which is will look like this. It's not about color, it's about the size. Right? That's what we get. All the spectral peak you get, they are Gaussian graph. You get a constructive interference. So this is one Gaussian, this is two Gaussian. You take their product, you get a single center Gaussian. So the new center will be here. This is Gaussian 1, G1, this is G2. Their center was, let's say this is R1, this was R2. You get a new Gaussian here, which center is capital R. Now let us look for scatter. How does scatter rules? Scatter looks like this. I'm sorry. Is exponential of minus x, right? It
Yes.
looks like
Yes, sir.
just this one. Another slater will be looking like similar way. Let's say start is a sigma 2 is less, so it look like this. Now if you take this product of this function, that will never going to look like another slater. To take product, what I get somewhere in between. Here I get less, then here I will be getting more. This function will dominate. Right? So two slaters can never multiplication of two slaters cannot be a slater. That's it. Did you get a qualitative answer?
Yes, sir. Yes.
So that makes the calculations much more easier. Okay? Now next question is that's fine. Now how many orbitals we are going to take? How many atomic orbitals we are going to take? If you take number of as many number of electrons are present in each atom, it's just as MO theory, LCA. But that does not give us a good result. You need as many as possible. How many? Now chemists came up with a much better idea. They will not take arbitrary large set. You see, you can take arbitrary large set. From physicists, they are just atomic, they are just one electron function. You take a number of that. You should get a result. But physicists are smart, the chemists are much more smarter because they understand molecule. They came with idea why to have taken an arbitrary large number? Why not choose our function such that with small number give me a good result? And that information comes from just looking at the molecule. You take water molecule, you take so water molecule, we know oxygen has at the occupied level 1s orbital, 2s orbital, 2p orbital. You see, this is hydrogen like orbitals. But we know from our VSPR theory, valence bond theory, or the MO theory that gives 90% correct, at least qualitatively correct result. So we take functions that looks like s orbital, p orbital, d orbital. So we'll take a Gaussian function, but just not Gaussian. Gaussian will multiply it by the power of x, power of y. So we call them p-type Gaussian. If power of x plus power of y plus power of z equal to 1. We take d type, we take f type, and so on. So you design your basis set such that with limited number of basis set, you get good results. You get a conversion. That's what we call basis set. Now, obviously, the way you think you design a method to construct basis set, and the way design a construct basis set, they may not be same. And that also depend on what kind of atmosphere I have. You see, oxygen in carbon dioxide will not have same property of oxygen as formic acid. These two are different, right? So you design your basis set based on what kind of calculations you are going to do. So the basis sets are not unique. There are many. Some of the well-known popular are Popol basis set, Dunning basis set, and some other. Diksha knows much more about it. You can take n number of different type of basis sets and then find out which basis set with less time give you the good result, more accurate result. Okay? So these days also we do similar that kind of calculations to find a basis set for a certain level of theory. Of course, if you keep on increasing the size of basis set, results will become better and better, and after some time, the results will not change because of basis set. It converts. It doesn't mean that you got a correct answer. Let's say I'm talking about Hartree-Fock. There are two limitations. One, Hartree-Fock method itself has a limitation. This is single particle approximation, cannot produce the correct answer. Second, I'm taking the finite basis set to construct my f. Now, if I keep on increasing the size of basis set, I am improving f from the basis set, from the point of C. So once time will come at certain point, it will no longer improve if we keep on increasing the basis set. We said that is a basis set converse result. But that may not be accurate because Hartree-Fock itself has a limitation, has an error. Right? So for any method, all method has some sort of error, some sort of discrepancies. For any method, you can actually calculate the basis set convergence limit. Increase the basis set, find at what point it does not increase. With respect to that, you compare a result with a small basis set. You see how being a small basis set, how good it produces the result. Right? What you need to do, what kind of functions you need to incorporate there. So this kind of studies are still we are doing this kind of studies a lot to find out the optimum size of one electronic basis sets. Okay, so that's more or less complete the Hartree-Fock theory, right? So if you have time, if you have interest, really leisure time, and want to do, then you can start writing program for that. Right? You don't need to calculate the integrals; those are there. Those are available from any of these free packages. You need to know how to get those integrals for a given basis. You don't need to also get the basis set. That's there in libraries, free libraries. You can calculate from a given set of basis set. You can run a known package to calculate the electron integrals, and then you can write the Hartree-Fock code itself, the converters. Right? This can be done. A lot of people do that. A lot of universities in, I don't know in India, but a lot of universities in abroad, they make MSc student to write Hartree-Fock code. So, unless you don't love, it's a practice that people do. Okay, so some people who love that writing code. So this is common practice that MSc people do. And they don't have MSc, they have 4 years integrated, 4 years graduation course, BSc course. So that people do. India, we don't do it, as particularly chemist, we don't do. We don't like to write the program. But one can do that. If you want to become very comfortable with computation, then once in your lifetime you must write at least half of code. That will give you a lot of things. Whatever is, I mean, you are lagging back, whatever the loopholes are there, gaps are there, that will fill up once you write that. data are there. You can also find some codes written by some people and put in their blog. You read computational chemist blogs, you find the code. Whatever language you're comfortable with, you can write it. It's small, it will not take, it's not a very big code, small code. So that's about it. There are something also you should know when you write, if you write some code, then the integral calculations you can do. You can write your own code for integration. You can take from the library, but you can also write them. Right? The uh, using Gaussian has another advantage. You don't need to calculate all integrals. They have symmetry. They have eightfold of symmetry. For example, I have this. Let me write this guy. You see, if you change one and two, this become exactly same. So this will be exactly same as if I write sigma nu delta mu. This will be exactly same as mu sigma. This is exactly same as their Hermitian, their complex conjugate, their Hermitian. So this will be exactly same as delta mu sigma mu, which is equal to mu, right? And then since their Hermitian each function is a real function. For electronic calculation, we don't use complex function. All functions are real. Since they are real function, this and this also you can alter. You can exchange. So you get eightfold of symmetry. How many integrals are possible for a given say? Let's say if I have 100 bases, one electronic functions, I get this many. So each will run from 1 to 100. So I have 100 to the power of 4. What is that? That is approximately, and that is equal to 10 to the power of 8. But you don't need to do these many. The order of this is equal to, this is order as right as 4 by 8. This is the order. So basically you need to calculate 10 to the power 8 divided 10 to the power 8 divided by. But it does not look very attractive, but it is actually attractive. You are reducing a computation by 8 times. Right? You don't need to really bother about how to calculate the integrals. Very few people are doing these days. I know one person, Walid, he does still. He write code and develop algorithm to compute the integrals faster and faster. But many of the efficient, he has a free package. We distribute those codes. You can just take from there. No matter. Most of the packages they have very fine algorithm to compute the integral. You can just run them with a limited time. They don't take much time. 100 calculating integral with 100 basis set basis function does not really take more than a minute. So that's why the computation become much more feasible. Whatever calculations you do starting from Hartree-Fock, MP2, TFT, any calculations you do, you need to calculate these integrals. That's the starting point. Okay? Not one time, many times. If you are doing optimization, as I said, it started from a fixed geometry. There you calculate the electron integral. Then change the geometry, you calculate another set of integrals. You keep on doing it. You till you get the converse results. Right? You get the optimized structure. And basically, this is how the Hartree-Fock theory is. This is the starting of Hartree-Fock theory. Okay? I mean, this is the end of Hartree-Fock theory. This is the starting of electron structure theory. We are not end here. Everything we do after this is to improve Hartree-Fock theory. The advantage of Hartree-Fock theory, it gives sometimes you are 99.9% accurate. Now, question is that for 1%, 0.1%, why you need to do advanced theory? And that's 1%. And also, we say you can never get 100%. This is a dilemma that chemist has. I have, I know I don't get 100%. I know I got 99.9%. Then rest 0.1%, why should I bother? But you see, chemistry lies on that 0.1%. From a physicist point of view, that's just 1%. From a chemist point of view, that whole chemistry is there in that 1%. Is a difference. Chemists are never interested in the absolute total energy. We always deal with the difference in energy. So if you are doing a reaction, A is going to B, you calculate energy for A, calculate energy for B. Let's say A is 99.9% accurate, B is 99.95% accurate. You subtract that, you get an error. Right? If this error can be, if the reaction can be is exothermic experimentally, this error can be endothermic. I mean theoretical. So what you are expected to get, you may get a complete opposite results. So the difference of energy is most important, and all error accumulate in the difference. They don't cancel. Sometimes they add up. So you have to do much more advanced theory to get close. I mean, better and better results. How close? How good? As good as possible. Yes. Any question from that side? So that's why the rest of the 1% or 0.1% or 5%, whatever left out is important. We have to do lot of theory. You see, artifact theory, Wuhan equation particularly, it came around 30s or 40s. And after that, something like 90 years, people are at least 60, 70 years, people spend to improve artifact. They're still doing it. It's just to capture that 1%. So you must understand the importance of 1% and how to get that 1%. Again, everything except very few, one or two methods. Everything start from artifact theory, and our goal is to improve artifact. So we started with 9%. We are not starting with arbitrary 1% or 0% or 50%. The variation theory artifact is extremely useful, important. It gives most of the energy that is required that such system has. Rest will run behind those. Okay. So there are two factors that we have to understand. The before wrapping it artifact theory completely, there are three things you have to I mean, couple of things you have to understand. What could be the possible reason of not giving 100%? Right. One is of course not within context of artifact theory, but not really beyond artifact theory. You see, after doing the spin integration, after getting the Ruthan equation, if you remember, I wrote a function chi I, let's say R1. This you have written as psi of I. This was not R1, sorry, this is X1 or spin coordinate. This is psi I of R1 and alpha omega 1 or psi of or and psi of R1 beta omega 1. What does it tell? It tells chi I will have two orbitals, will have same space but different speed. Right? So after doing this, according to Alpha principle, when you fill the electrons, two electrons opposite spin, you accumulate them in the same spatial orbit. Right? If they have same spin, you don't do that. You put them at two different orbitals itself. So space for two opposites, two same spin, they are different. Space for two same spin electrons, they are same. But is it physically correct? Of course not. Two electrons by no circumstances can occupy same space. You have in Hamiltonian, you have 1 upon Rij. Right? If R is same for two electrons, it becomes Rij becomes 0. 1 by 0 is singularity. It's not possible. So main problem of artifact theory is this. Right? Due to Coulomb potential, two electrons should always avoid each other. Right? This problem is called Coulomb hole. What it means, the moment one electron sees another electron, it sees nearby a big hole. Like If I go here too close to him, I must fall on the hole. Right? Another hole is there. When one electron sees another electron with same spin, they will always avoid each other. Two electrons, same spin, cannot occupy same space. So the moment electron 1 sees electron 2 with same spin, when approach to approach to this one each other, you find a weak deep hole here. They cannot go. Right? So there are two holes. One is Coulomb hole. One is Fermi hole. Right? This Fermi hole is already taken care of in the Hartree-Fock theory. In the Hartree-Fock theory itself, we don't allow two electrons having same spin occupied same space. We don't do that. But for Coulomb holes, we don't take care of Coulomb holes in the Hartree-Fock theory. So that is the problem. We have to do something to take care of that. So that two electrons, the moment they try to come close each other, they avoid. They go. Right? So two electrons, moment like this, they'll go up. Where can they can go? Actually, I'm having two electrons coming close together and they have to avoid. If they avoid, why they can go? They can go to the virtual orbitals. Right? So what we'll do, we'll take the virtual orbitals, fill this electron to the virtual orbitals, and that will also construct determinants. We'll add those determinants to our Hartree-Fock, to our ground state to get the exact description. Right? Those determinants are called configurations. How two are connecting, that is the configuration interactions. Mathematically, I will tell in the next class, but that's what it is. Hartree-Fock theory, by problem is of Hartree-Fock theory, does not consider the Coulomb. Any correlated theory you consider, you have to take care of Coulomb. How accurately you are considering you are treating the Coulomb hole. If you treat it more accurately, the resultant theory will become more and more accurate. Okay? So that's the limitation. And there is another limitation for not for Hartree-Fock theory, but Hartree-Fock-Ruthven equation. Equation comes from here. What we have done here, we have for two orbitals, we have put one electron here, one electron here, meaning that two electrons we consider same space orbital for them. If you don't do that, there's no restriction that I have to consider same space orbitals for two different electrons. I have to do that. We do that because the computation become half. Remember, gain become n by 2. But if I don't want to do that, I can still do it. Right? So what I have done here, this can be written as chi of ixi can be written of psi I alpha 1 omega 1. For the beta, instead of using same function, why I don't use another function? I can do. So these functions and these functions will be different. What is the problem? Problem is the diamagnetic. So when you diamagnetic, these two functions become exactly same. When they're paramagnetic, they become different. So make your functions as that at small distance, at equilibrium, they become exactly same. At large distance, they become different. There are a way to do that. That was done by Popel and Nesbet. That theory is called unrestricted artifact theory. What you do in unrestricted artifact theory, you consider different space orbital for alpha and beta. So in that case, we have a set of spin orbitals or space orbital here, we have set of space orbital here. And then you put electron here, and so on. Right? Why this is important, why this was done, because for a practical reason, you see a hydrogen atom, hydrogen molecule here and here, at equilibrium, experiments support that is doublet, right? So if I write this at equilibrium, I get this is a function, there are two electrons occupied Now what happened? If you have hydrogen atom, hydrogen molecule, right? If you give energy, what will happen? It will go up and up. After some time, it will break. So if you put enough energy, it become hydrogen atom and hydrogen atom, right? Now here is a big problem. That's one of the problem that Einstein did not, I mean, accept quantum mechanics. You see, I have one hydrogen here, one hydrogen here with the bonding distance. I have one electron here, one electron here. It's not really there. It has a probability, right? And then what I have done, I'm trying to see the moment it formed to hydrogen radical. Both the hydrogen radical will have same spin. Why will have different spin? Now here's a big problem because you have at the equilibrium two electrons upspin and downspin, and you are trying to take away from each other. Right. So at the bonding distance, you have to flip it, but quantum mechanics does not allow that. You cannot flip the spin. For that, you need to give additional energy. Where are you getting that energy? Right. So Hartree-Fock, restricted Hartree-Fock theory, and we know that this is an experimental fact. Once you break hydrogen molecule, it becomes two hydrogen atom. They are having same spin. So two opposite spin, how come at separate distance become one alpha, one beta? So if you calculate Hartree-Fock theory for the simplest hydrogen molecule by changing the internuclear distance, what you are expected to get, you are expected to get a graph like this, right? At the dissociation level, that will break. But what actually you get is something like this. The lower will be same. Because this is that additional energy which makes two electron bind each other with opposite spin. You have never provided or taken out of that energy to make it doublet or two radical, right? So Hartree-Fock theory, this will be restricted Hartree-Fock theory. This is, let's say, exact. You don't get Hartree-Fock theory cannot explain the dissociation limit. However, if you use unrestricted, their spin are not two electrons don't occupy same space orbital. At the lower equilibrium, these two orbitals become similar, right? So it explains the fact that at the, I'm not drawing up as per the scale, please forgive me for that, but this will be, no, I'm sorry, that's a problem, a basic mistake I made. A fundamental mistake I made after talking too much. I should not have done that. So this is my graph. Let's say this is the graph dissociation graph. This is the distance or internuclear distance. If I do exact calculation, it should look like hard should not be there. Now, if you do Hartree-Fock theory, you get energies which will be higher than, you get something like that. You get something like this. If you do unrestricted Hartree-Fock theory, you will be getting similarly. This part is very similar. Like not happening in this case. It will also be at the ground state and nearby ground state will be same. It can go through the dissociation, right? So that's the advantage of unrestricted US method. It can calculate the radicals, radicals and minor. However, there is a problem with UHF. The resultant functions are not spin adapted functions. They are not eigenvalue of spin operator. since you have two electrons, can two spin orbital can have two space part, you can show that the resultant unrestricted Hartree-Fock functions, they are not eigenfunction of spin orbitals, operator, and that's a problem because experimentally it should be eigenfunction of spin operator. Okay? So UHF, it can explain the dissociation limit, which is which are restricted Hartree-Fock cannot. But still, we don't use UHF unless it's really necessary to. We use RHF. So let's stop here. We will just have a look over whatever we discussed over last 1 month. We'll start here. From here, we'll start. Let's first we'll give introduction to CI method. Okay. From CI, we'll do up to CISD. One thing I did not yet cover, I forgot, is population analysis and calculating the properties. This is fine. This gives us energy. But what if we want to calculate dipole moment? Equally calculate dipole moment, right? Or polarizability or any other molecular property. Okay, how can we do that? And second is the population. Can we get a qualitative estimation of how much charge one atom will have inside a molecule? This is not a nice question. Because once you form the molecule, the atomic existence are not there. They are part of atom. But as a chemist, we like to associate some charge on every atom. Right? We always prefer to put delta minus and delta plus. Theoretically, those doesn't make any sense. I mean, in the absolute sense. Why oxygen will have more negative charge? That means electrons are localized there, but electrons are not localized. So ideally, I should not put. You see, with physical chemists, we get irritated by looking organic chemists putting that arrow. They put the arrow happily if the electrons moving from there to there. Electron does not move there to there. They are just probability. So, but as a chemist, it's chemists are more intuitive, right? Intuitively, can we say if for a molecule, if nucleophile attacks, which center it will be attacking? So we prefer to put some charge of every atom, right? From artifact theory, you can do that. So there are few types of population analysis, but the first one and still widely used, although not very good, is called Mulliken population analysis. We are associating a charge on every atom. We can also calculate that from the Hartree wave function. So next class I will just briefly tell how to do that. Mulliken and Levin I will tell. There are many. Okay. People use each one has some advantage, some disadvantage, but they all are qualitative. Nothing is quantitative. So we'll do that and then we'll move to the CI method. Okay. And I'll see you next class.
Okay, sir.
Okay, Diksha. Yeah.
Okay.